Okay, part 3, Myra. So part 2 and part 3 are both about variations of perceptron. And Myra is kind of along a different motivation. Um, so Myra says that one of the biggest problems in perceptron is that perceptron often makes too bold or too small updates. Too bold update that is overcorrection and too small update that is undercorrection. So for example, this is the example from week 2 where we demonstrated one-step update of perceptron, and maybe many of you have noticed that this is undercorrection. What does that mean? Well, it means that after correction, after this update W prime, the new W, the new weight vector, still misclassified this example X. Okay, this current weight vector misclassifies because this X is positive example. But after this, even after this update, the new weight vector would classify the plane in this way, that this is the new decision boundary, and it will still misclassify this very example X. So in other words, the update is too small. The learning rate should probably be 2. If the learning rate is 2, then your new weight vector will be somewhere here, and that would correctly classify this example. And in this case, it's overcorrection, and overcorrection is actually more common in practice than undercorrection, and that's the original motivation of Myra, just to kind of avoid undercorrection, sometimes avoid overcorrection, and at the same time, fix undercorrection as well. In this example, for this particular positive example X, the current weight vector W misclassifies it for sure. Now after you update this way, right, W plus X is the new W vector W prime, you correctly classify this example, but probably a little bit too much. Okay, so if you just want to correctly classify this example, then updating to somewhere here is enough. Okay, but that's just the new weight vector will be perpendicular to or orthogonal to this positive example X. That's probably not enough. You probably need to be a little bit safer, allow some margin, some safety net, buffer zone, right? So in Myra, we want to make sure that after update, the new weight vector W prime dot product X will be exactly 1 for positive example, or exactly -1 for negative example. Okay, so that 1 is the margin, is the safety net. Okay. So the update equation is W prime is W plus, instead of Y times X as in vanilla perceptron, we would do some modifications here, which kind of effectively tune the learning rate. Okay, but it's not like some learning rate that you tune yourself. It's kind of automatically set by this magic equation. But this magic equation, although it looks very complicated, it's actually very simple geometrically, and you can work out the derivation of that in geometry, which you will do in the next homework. So basic idea is that this distance is 1 over x, and this distance is the dot product divided by x. So this exactly is 1 minus wx over x, over the norm of x. And you just need to scale the scale the input vector x to this length. Okay, so that's how you scale it. You divide it by its length, its norm, and times the x again. So then you will create a copy or a kind of a shrinked version of the x vector, whose norm is exactly 1 minus w dot x divided by the norm of x. Okay, that's the exact enough update. Okay, let's look at the undercorrection example in more detail. So we said that W prime is undercorrection, and we need to make it at least pointing to somewhere here that at least agrees with this example X. So you want to make sure that after this update, at least this problem is solved, right? Okay, so Myra says I'll do it here. So perceptron says I'm here. Myra says I'm here, right? And this distance is 1 over norm of x. That's the safety net, right? So here's an important concept. There are two concepts of margin. One is functional margin, which is just a dot product, and the other is geometric margin. That is the dot product divided by norm of w. Now, In Myra, we want to make sure that after update, functional margin becomes 1. Okay, we cannot ensure the geometric margin, but we can ensure the functional margin is 1 after update. That's the definition of just enough update. Okay. Now, if you remember the linear separation condition in perceptron convergence proof, we said that there exists a unit oracle vector who can separate each example by at least delta. So that delta is functional margin because that's the dot product, but it's also a geometric margin because we assume unit oracle vector. So in that case, this W is unit, which means its length is 1. So that's another reason why we chose unit oracle vector. And here, we can see that you can rephrase Myra as a optimization problem. That is, you want a minimum change to your current weight vector, W, right? So minimum change in terms of Euclidean distance, okay? Such that after this update, you have a functional margin 1. So that's another way of kind of explaining Myra. And this way is very much inspired by and similar to SVM. Okay, and next week we'll look at SVM, and SVM will be a global version of Myra. Myra can be viewed as a one-step or online version of SVM, where you just try to minimize the distance between the new wave vector and the current wave vector. In other words, you want to make the smallest change. Why do you want to make the smallest change? Well, because that's stable, right? You don't want to make very bold changes. Then you fluctuate. Your model fluctuates. You want to make very small change, just enough. What is just enough? Well, ensure the functional margin or dot product becomes 1 after update. Okay, so that's why. So this is the smallest change here, and this line is basically, the boundary where it's enough, right? Above that line, it's kind of more than enough. Beneath that line, it's less than enough. So you just make it to here. That's just enough. Okay. And the geometry of this is very beautiful, and you can work it out yourself. Now, if you switch the coordinates of your, if you look at the projection of W on x, then that's 1 over this norm of x. But if you look at the projection of x on W prime, on the new weight vector, and that distance is 1 over W prime. And that explains why the geometric margin is the dot product divided by the norm of the weight vector W instead of the norm of the input x. Okay, so this line is the line where defined by, it's basically the separation boundary or decision boundary defined by the new weight vector after update. So W prime dot product x equals 0. Now this line is where W prime dot product x equals 1. Okay, so that means this particular example, x currently has a functional margin of 1 after this update. Okay, and its geometric margin is 1 over norm of W, or length of W. Okay. Now, another kind of even better algorithm is called aggressive Myra. It's very much like Myra, but it would be more kind of aggressive in doing preemptive updates. What does that mean? It means that you would update even if it correctly classifies the current example, even if the current weight vector is correct in terms of this current example, but not confident enough. What does that mean? It means the functional margin is not big enough. We want a functional margin to be at least p, and p is some number between 0 and 1. Okay, for example, if you look at the next example, next positive example, this x, particular x, it's currently correctly classified by this current weight vector W prime after the last update, right? But it's probably not enough because its margin is smaller than what I wanted. I want the functional margin to be at least 0.7. Okay, let's say p is 0.7, and this example is not enough. Right? You need to fall above that line, okay, in order to have a functional margin of at least 0.7, but you currently don't, okay? And then I would update. And how do I update? Exactly the same way as Myra update equation. In this case, Myra is a special case where P, the aggressivity parameter, is 0. That means I would only update if this current example is misclassified. So I have very high tolerance for Myra. So Myra says, as long as it's correctly classified, I don't care about margin. But aggressive Myra says, even if you correctly classify, but if your margin is too small, I still update. Okay, and aggressive Myra is even more like SVM. So there's a kind of a progression from perceptron to Myra, which is in between perceptron and SVM, and aggressive Myra is in between Myra and SVM. So it's even one step further towards SVM. And SVM can be viewed as aggressive Myra, where P is very, very, very close to 1. Okay, so larger P leads to larger geometric margin at the end, but much slower convergence. And you can see the demo here. So this is the exact same demo that I wrote in Python. And this is perceptron, which has very, very small margin, almost touching these points. Well, Myra has slightly bigger margin, but really very small as well, because you can tolerate this example if it correctly classifies this example. But aggressive Myra says, no, you're not good enough. I need to be a little bit further from you in order to be safe, right? So aggressive Myra, 0.9 aggressive Myra, which is very, very aggressive, has this separation boundary, which is almost like optimal margin, right, if you can see it. And this example as well, so perceptron is almost 0 margin. Myra has a little bit of margin, but not too much here. And aggressive Myra, 0.9 aggressive Myra, is enjoying a much better margin. And I can show you some demo. Right, so again, this is aggressive Myra, and these two are Myra and perceptron. You can see aggressive Myra has much better margin, much larger margin. Yeah, much larger margin, right? Much larger margin, meaning that it's far from both sides, both positive and negative sides. Right, and perceptron is the worst. Aggressive Myra is very good, but it converges much slower, right? The convergence depends on the aggressivity parameter P. Right, in every single example, you can see that aggressive Myra enjoys much larger margin. Okay.